Alright, we're going to take a look at part 5b, question number 18. We're going to continue our work from part 5a on applications of differentiation. We took a look at problem 17 and the steps to solve that problem in the previous clip. Now we're going to take a look at question number 18. So for question 18, let's say we have the function g of x is equal to 4 minus 2x over 3, and the interval is actually 4 plus 2x over 3 on the interval 1 to 5. The instructions here are the same as problem 17. We are to look for the absolute extrema. Okay, so let's go ahead and specify that. So what we're looking for is we want to find the absolute extrema. So when we're talking about absolute extrema, as indicated before, we're talking about the minimum and the absolute maximum. If we want to find the absolute extrema, we're going to make use of the CVEPS procedure. This was broken down on the previous presentation. If you don't know what this means, you can take a look at that for the detailed explanation. Okay? Alright, so let's get started with part 1, the CV part, which is to find the critical values. Okay? What are the critical values? The critical values are basically points where the derivative, well, in this case we're looking at g prime of x, where g prime of x is equal to 0 or g prime of x does not exist. Okay? Now let's take a look at what we're dealing with right here. This is a polynomial function. Even though it does not look like a polynomial function, it is a polynomial function. And polynomial functions are smooth and continuous, so there isn't going to be a point where the derivative is non-existent. Alrighty, so let's go ahead and find the derivative. The function is 4 plus 2x over 3. Now we want to find the derivative, g prime of x. So it's basically the derivative of 4 plus 2x over 3. Now, do we have to use the quotient rule here? We have the quotient of two functions. Do we have to use the quotient rule here? Remember, you never want to be in a haste to apply the quotient or product rule. You always want to ask yourself, is there a way I can simplify the given problem in order to just use the simpler differentiation rules like the power rule or trigonometric differentiation? So in this particular case, we can rewrite it in a way where we can avoid using the quotient rule. So let's rewrite this. If we write this function, we can write its derivative as 4 over 3. So just decompose this function, 4 over 3 plus 2 over 3x. Find the derivative of that. So you can clearly see that this is just a linear function. Okay? A linear polynomial, slope of 2/3 and y-intercept of 4 over 3. So if you differentiate this term by term differentiation, you look for the derivative of 4/3. Apply the power rule there, and then you can factor out 2/3 and find the derivative of x. We don't have to use the quotient rule. Okay, this is a constant, so the derivative is 0. Plus, if you differentiate x, you get 1. So plus 2/3 times 1. The derivative here is 2 over 3. Alright, so we have now found the derivative. G prime of x is equal to 2 over 3. Now, we're going to proceed to find the critical values. Okay, so we want to look for where g prime of x is equal to 0 and where g prime of x is non-existent. Okay, so g prime of x is equal to 0. We're basically looking for where 2/3 is equal to 0. So 2/3 can never be equal to 0. there are no points on the function where the derivative is equal to 0 because the derivative is fixed as 2/3 for the entire function. Where is the derivative undefined? Nowhere, because it's always defined, namely 2 over 3. What does that mean for us? It means that this function does not have critical values. All right. So we have the CV part taken care of. Now let's specify what the endpoints are. Our endpoints are going to be x equals 1 and x equals 5. Those are the endpoints. Alright, so let's move on to the P part of CVEPS. P represents potential extrema. Alright, so how do you find the potential extrema? The potential extrema are basically the combination of your critical values and your endpoints. Since there are no critical values in this problem, the endpoints will be the potential extrema. So the potential extrema are going to be x equals 1 and x equals 5. Okay, so let's go ahead and describe what these extremas are. Whether they're relative max, mean, or neither. To do this, we're going to use S and CVEPS part 4. S represents the sign chart. Okay, so you're going to be making use of your fun chart here. F-U-N, concave up, concave down. F prime is increasing where F is concave up, decreasing when F is concave down. F double prime is positive when F is concave up, and negative when F is concave down. When F is increasing, F prime is positive. When F is decreasing, F prime is negative. Okay, so there goes our fun chart that we're going to be using to describe the behavior of this function around these endpoints with the after determining what the sign is. Okay, all right, so let's go ahead and create our interval. So our interval goes from 1 to 5. We have only one interval in this problem, so it's going from this endpoint, which is 1, to the other endpoint, which is 5. Okay, so we want to see what kind of extrema these are, the endpoints, if they are any at all. Okay, so to do this, we're going to be looking at the sign of f prime and connecting that to the behavior of f. Okay, so we have down here, we're going to be looking at the sign of f prime, no, in this case g prime, positive or negative, and connecting that to the behavior of g of x. Is it increasing or decreasing? Bottom line. Alright, so this is 1. We have only one interval here. And we are going to be, let's pick a value. Let's use x equals 2. Okay, so the question is, what's the sign of the derivative when x is equal to 2? So we're looking for g prime of 2. We know that g prime of x is 2/3. Okay, we already did that, right? G prime of x is 2/3. So g prime of 2 is basically 2/3 evaluated at x equals 2. 2/3 is a constant as independent of x. G prime of 2 is going to be 2/3. What we care about is the sign. The sign is positive. Okay, so using the fun chart, when g prime is positive, what is the behavior of g? So you look at your fun chart right here. When the derivative is positive, the antiderivative is increasing. Okay, So when g prime is positive, that means g is increasing. So if g is just increases from this endpoint 1 all the way to 5, can you describe what the extremas are in this particular case? If you're increasing from a point, you start from a point like the ground and head upwards, guess what this is going to be? We'll know for a certainty that this is a relative minimum. Okay? It ascends to this point, which makes this a relative max. Okay, so what more do we know about these two endpoints? Okay, since this function is increasing, strictly increasing from 1 to 5, and it's a polynomial function which is continuous, there are no discontinuities there, we can use the extreme value theorem to arrive at a conclusion. Okay, so the extreme value theorem just basically says that if a function is continuous on a closed interval, then it has an absolute maximum and an absolute minimum. So since these are the only two extremas that this function has, guess what? Based on the extreme value theorem, we know for certainty that this min is the absolute min, and this is going to be the absolute maximum. We're going to verify this by a check in a second, all right? All right, so let's go ahead and provide the explanation or the justification as to why these are the extremas that we indicated that they are right here. So let's partition our workspace. We're going to start with 1, okay? So since g prime of x is positive to the right of the included endpoint, what's the included endpoint? X equals 1, that's the right endpoint, the left endpoint, sorry. What does that tell us about the behavior of g? Since g prime of x is positive to the right of the included endpoint, that tells us that g is increasing from the endpoint x equals 1. And what does that make? What kind of extrema does it make this endpoint? Well, it makes x equals 1 a relative minimum. X equals 1 is a relative minimum. Okay, because you're starting from a point and you're ascending upwards, so that makes your starting point a low point or relative min. Okay? Alright, how about 5? What's the story there? In that one sense, g prime of x is positive to the left of the included endpoint, x equals 5. What's the behavior of g? As it approaches that point, g of x is increasing to that point, is increasing to the endpoint x equals 5. So it's like you're ascending to a particular value. Okay, so when you ascend to an endpoint, what do you classify that endpoint that you're ascending to? If you're ascending to an endpoint, that's going to be a relative max. Okay, so that tells us that x equals 5 is a relative maximum. Alright, so that's our S step. Now let's finish it off with our check, just to check to verify that our claims are correct. So let's do our check. The original function f of x is 4 plus 2x over 3. So let's start with the first one. F of the minimum, 1, that will be 4 plus 2 times 1 over 3. And then we have 4 plus 2, which is 6 over 3, which is 2. Okay, and then f of the right endpoint, 5, is 4 plus 2 times 5 over 3. So we have 14 over 3. Okay, and then we can write this as a mixed number. This is going to be 4 and 2/3. Oh, and then another point to indicate here, by the extreme value theorem, what do we know? By the extreme value theorem, x equals 1 is an absolute minimum, and x equals 5 an absolute max. So absolute max. Okay, so these are the locations of our extrema. So let's just put the words at there. So at x equals 1, we have an absolute min, and at x equals 5, we have the absolute maximum. So let's put at there. All right, so let's finish everything off. Absolute, we have an absolute minimum value. Absolute minimum value is what? Absolute minimum value of f of x equals 2 occurs at x equals 1. And we have an absolute maximum value. F of x equals 14 over 3, or you can use 4 and 2/3. And that happens at x equals 5. So these are our absolute extremas for the function provided in the original question.